clays, local clays that they use, and they have different properties of the terracotta from that. After it's unmolded, then it's cleaned up and glazed, and then put on carts and put into a tunnel kiln and fired. And then boxed up and ready to ship. So how is it used? As I said, it's used for cladding for a lot of different buildings. It was originally became popular because it was easy and cheap. And so we didn't have as much of a tradition of stone carving in the US and in the West as maybe you'd have in Europe. But with terracotta, you can just carve one piece and then make more and more pieces from that. So it's kind of ironic that at the time it was originally kind of a cheap imitation for stone, and now it's a very expensive material that we're trying to restore and retain. The glaze allows all different kinds of colors. When it was originally made, it was advertised as needing no maintenance, and the glaze was thought to be completely impervious, so there wasn't a lot of thought given to flashings or waterproofing. It's also fire resistant, so it's often used for cladding. I have a couple of pieces up here. You can see now that this is a piece of old terracotta from St. Dominic's Church, and it has a really red bisque or clay body, and this was actually manufactured, I think, in Seattle, in Washington State. And so it's a little different than what we usually see on most of our buildings. It's kind of this yellow color, and this is gliding bean terracotta, a new sample of a new piece, and then this is a piece from 140 New Montgomery. So this shows how it's used. This is a section of a typical cornice, and here you can see, and this is actually a block being put into place, a block of new terracotta. And so in the photo, you can see that end of the block right here is the web, and then here's the face shell of it, and then it has other intermediate webs that go back, but it's basically unfilled. It's anchored. Terracotta is usually anchored with secondary steel. And back in the day when it was popular, in maybe the 1920s, it's just anchored with all mild steel, which unfortunately can corrode. So all these red arrows point to the different J-hooks and bars and pieces of mild steel. Early buildings, they didn't have flashings, but then the National Terracotta Society, which was a group of terracotta manufacturers that got together to write standards and kind of improve the practice, published a standard in 1927. They published specifications, and they did indicate flashings at that time. Another thing about terracotta buildings is the wall systems were not detailed for any kind of differential movement or expansion and contraction, and that'll become important later when we talk about different problems that terracotta has. So how does it fail? Probably the most common type of failure we see are what we call glaze spalls. And that's where little pieces of glaze start coming off, and then eventually you can lose lots of the glaze of the terracotta. There's a lot of different reasons that you can get glaze spalls. I think the most common one in California is that water gets into the clay bisque somehow through a little crack or open joint or something, and then it's trapped behind the glaze. That is the perfect environment that algae likes to grow in. So you get algae growing underneath the glaze, and then it eats the clay bisque, and then you get slime mold that grows there and eats the algae. And so you have this whole little garden growing under your glaze. And you can start chipping out around a glaze spall that you see, like I'm doing there on the right, and you'll just get more and more of the glaze that's loose and has algae under it and that comes off. So that's one reason. Another reason that we see less commonly is poor glaze fit. So that you don't see it anymore because the manufacturing of terracotta is so much better. But if the coefficient of thermal expansion of the glaze and the clay is different, then it has poor glaze fit. And as it goes through temperature changes, or even just as it comes out of the kiln and it's cooling off, the glaze can spall off. Glaze Crazing are those fine little cracks that you think of, like you might see on an old, Chinese vase antique or something like that. But we also see those on terracotta. And I think those are caused during manufacture by a difference in contraction as the clay and the glaze is cooling. And they're not, I've found that they're not usually problematic. I don't usually try and do any repairs to the crazing, because if it's just small, fine cracks like that, you can just let them be. And they're usually so small that water can't really get in there. Another problem is bisque spalling. Probably the most common cause of bisque spalling is corrosion of embedded steel. So a lot of terracotta, as I showed you before in that cross section, is hung from mild steel, and then water gets in. As steel corrodes, as you know from this morning, it expands, it takes up more space, and it expands enough that it can crack and spall the terracotta. Terracotta can also spall from freeze-thaw expansion, expansive properties of the clay, or an accumulation of salts in the terracotta. So sometimes the failure of terracotta is really subtle and really hard to see. This is a building in San Francisco that I was just up on last year. Oh. Okay, now I got to go back. There we go. And so I was on a swing stage really close to this, and I could see these cracks. And I was with a contractor. We were doing some emergency stabilization of loose pieces so they didn't fall onto the street. And I said, well, let's just try and put some stainless steel anchors in this to hold it on. And so he was getting ready to drill, and just this whole chunk of terracotta like this, which is about as big as my arm, just kind of came off in our hands. So it's, to understand what's going on with terracotta, you really have to get up close to it. And I think you'll notice a theme as we go through here about terracotta failures. The enemy of terracotta is really water, and water getting into the terracotta and into the backup. Okay, so this is a quiz for you guys. Let's see what you know. So, sorry. This is a high-rise building in San Francisco, clad in terracotta. You see these vertical cracks like this going up a column. Why do you think it would crack like that? How long? No, what? No, why do you think the column is cracked like that? Why would you get vertical cracks? Right. It has a steel column behind the terracotta, and that steel was corroding. So here's the steel column, and you can see the cracks coming right from that corroded steel column. Okay, next one. This one's much harder. Here's another terracotta building, vertical cracks in the columns, a little bit of buckling of the terracotta. Any guesses as to why that would occur? Movement, that's true. Okay, so terracotta grows over time, like all fired clay products, like brick, but it grows much more than brick. So when you take a piece of terracotta out of the kiln, it's the smallest it will ever be. And over time, it's just going to grow. This was a concrete frame building. Concrete shrinks over time. As you put load on, when it dries, it shrinks. And then as you put load on it, it also shrinks, doing something called creep. So this building had no provisions for expansion and contraction. And it was basically tearing itself apart because the frame, the internal frame, was shrinking and the terracotta was growing. Yes. There was also a problem with shelf angles that didn't quite reach the corner. And I've seen this I haven't seen as commonly, but I've seen it before. The shelf angles are a pretty common problem. So a lot of times you'll look at a brick or terracotta building, you'll see these vertical cracks right up the corner. And it's because they didn't know what to do with the shelf angles coming from one side and the other side, and you get to the corner and they don't quite meet and there's no space for them. And so then you have every story of terracotta supported on the shelf angle in the middle of the wall, but at the corner, it's just kind of stacked up from the ground. And those things are going to move differentially. Okay, here's the next one. This one's a little more unusual, a little trickier, but if you notice the red spots that I put on the bricks, that might give you a clue if you know how brick walls are typically built. There is a column going down through the middle of the bricks, and when we first saw the cracks, we thought, oh, that column's corroding. But then we did our openings, and the column was not corroding. So what was causing the problem here? Right, right. So these are header bricks, and they should go back through a couple of wides of brick. But in this case, they didn't. They were false headers. They just cut them off. And so there was no real attachment of brick back to the steel. Okay. Everyone who lives in California, this is a clue, should know what these cracks are caused by. X-cracks, yes. Earthquakes, exactly. And how about that? Also from an earthquake, that's pounding damage. So a lower part of the building pounding against the tower that it's built right next to. So I talked a little bit about shelf angles. Most terracotta that you'll see is on transitional masonry buildings, which are steel frame buildings with brick or concrete infill and then a terracotta cladding. And the terracotta rests on top of the shelf angle. Shelf angles and lintels, by their nature and their function, are really close to the outer surface of the wall. And that means that once water starts getting into the wall, they are the first things to corrode. And so they're really vulnerable to corrosion. And then when they start corroding, they'll crack the terracotta. All right, how do we fix it? So I think, as other people have talked about, before you can decide what you're going to fix, you have to know what the problem is. So you have to do some investigation. And then once you figured out what the problem is and how many of the problems you have and where they are, and then you can start designing your repairs. How the Secretary of Interior Standards applies. It allows for the repair and replacement of deteriorated features while maintaining the historic appearance. So generally, we try and repair rather than replace. Sometimes we have to replace features either because they're too deteriorated to repair or they're covering something that is the root cause of the problem. So for example, that column cracking that I showed you because of the steel underneath it is corroding. There's not really any way to repair the steel except to take the terracotta off, clean up and paint the steel, and replace it. As you know, there's 4 different Secretary standards. Rehabilitation is the one that we most often use that seems to apply to this type of facade repair. It allows for new uses that minimally change the materials and features and allows for compatible additions. So I guess I talked about this a little bit. So you want to diagnose the problem, maybe look at a range of different solutions. Try and repair rather than replace, and replace in kind if you can. Or there's a lot of substitute materials for terracotta, but you have to understand what are the ramifications, both visually and performance-wise, of using substitute materials, and then understand the visual implications and the durability of repairs. So there's a couple of different approaches. One approach is for, I guess, surveying a building, getting the project out to bid. One is to do a 100% survey. And we have done that, where we go and we look at every single block of terracotta, put everything on CAD drawings in the field using a tablet. The advantage of that is that you can get much more precise bids, and sometimes that's really required by public agencies who want to know exactly how many blocks am I going to replace. The disadvantage is there's a huge upfront survey cost because you have to get on a swing stage or whatever to get up close to the building and then survey every single block. And then even after you've done that, inevitably, you're going to take, something will happen during construction, like you start taking blocks apart and the backup wall isn't what you expect. So there's no guarantee that there's not going to be some kind of surprises during construction. The other approach is a partial survey. And to do that, usually we start with a binocular survey, pick out areas that we think, oh, this area looks suspicious, this area looks typical. and then do a close-up survey of a representative area. When we do that, we usually try and bid with allowances and unit prices, so that if there are more or fewer repairs, then that can be adjusted using the unit prices. So that has a much lower upfront cost, but the disadvantage is there's, I think, more of a risk of change orders during construction. Either way we do it, usually in our specifications, we put in a quantities table. And I think the important thing about this is that you need to decide on what your quantities are going to be and what your specs are going to say before you go out and do the survey. Because if you go out and you count, oh, I have 4,000 glaze spalls, but then your specs break it down into 2x2 inch spalls and 4x4 inch spalls, suddenly your survey doesn't help you. They have to be correlated. So you have to be surveying the quantities and the repairs that you're going to put in your specs. And this just kind of follows through with the same thing from a bid form, just putting in unit prices. This is a whole list of different repair techniques, but I'm just going to talk about each one of those. So the first one is stabilization, and that, of course, is when you go up and see something and it's going to fall on the street and you have to do something to stabilize it. There's all kinds of different straps you can use, wrapping features like that, putting up a sidewalk canopy to protect pedestrians. And those are all temporary measures. They need to be monitored and they're not a permanent repair. So along those lines, San Francisco has a new facade ordinance that was just passed in, I think, March or April of this year. The California Building Code requires that buildings be maintained in safe condition. That means the owner of a building can't have pieces falling off of the facade of their building. The purpose of the facade ordinance is to ensure that building facades are maintained and reduce falling hazards. So it clarifies the requirements that are already in the building code. Kind of a side benefit of keeping buildings maintained is hopefully there will be fewer pieces of buildings falling off in an earthquake, but it doesn't require seismic retrofit of facades or upgrading building facades. They just have to be returned to their original condition. It requires facade inspections on a 10-year cycle. I think the first cycle of buildings is due in 2021, so building owners have a while. In thinking about repairs, of course, we all want our repairs to be durable. If you ask me, durability and sustainability are almost the same, because if you do a repair and it's sustainable, then you're not going back and spending energy to keep working on that building. So one thing to think about is the durability of the different components in a repair. For example, putting a stainless steel edge on a flashing makes it more durable than if it was just the perma barrier. Using stainless steel for reinforcement rather than galvanized steel or mild steel makes a more durable repair, even though you can't see it, and those pieces are all hidden. Mock-ups are really important. We always define mock-ups in our specifications. They form the standard for the rest of the work. We'd like them to be done by the same workers who are going to work on the rest of the building. And no work, we always put in our specs that no work is to be done until the mock-up is approved by the engineer, architect, or owner. I did once have a contractor, and I went out to site to see the mock-ups, and he had written, in like big chalk across there, approved. And I said, who approved this? Oh, I did. So one approach to terracotta that's cracked but not too damaged to repair is to anchor it in place. And there's a number of different ways to anchor terracotta. They're discrete repairs. Before doing that, you really have to understand what's the structure behind the terracotta and what are the load paths and how are you changing that structure by anchoring it in place. A couple of different fasteners that we use to anchor terracotta. One is called Helifix, or it's a helical anchor, and I have one up here. threaded anchor, and I really like it because you don't have to mess with drilling a hole, putting epoxy in it. You just drill in the helical anchor, and it forms its own threads and it grabs onto the terracotta. Now we were doing some repairs on another building, that had previously been repaired, and we found these helical anchors. See, this one went through fine. This one, it just went up and bent against the terracotta. So I guess that's a good lesson to make sure that when you put the anchors in, they're really grabbing something. And so a lot of times we'll pull test a certain number of the anchors. Another type of anchor is our epoxy set anchors. Usually we use stainless steel threaded rods and fill the hole with epoxy and then put the threaded rod in. And we use those both to anchor existing and then sometimes to secure new terracotta blocks. Grout set anchors are for where you have more of a rubble wall and you can't really put in an epoxy anchor because you would just end up filling the wall with epoxy. And so this has a sock around the stainless steel pin and you fill it full of grout and it just fills up that empty space and anchors the facade. Expansion anchors, there's a lot of expansion anchors on the market, and sometimes we can use those to bond the terracotta back to maybe a brick or concrete backup wall. Most terracotta that we work on, we do a lot of patching of cracks and spalls and glaze spalls. If we replaced every block of terracotta that had a spall or a glaze spall, we'd just be stripping all kinds of buildings. So usually we patch the spalls. A lot of times we'll use reinforcement, so just little stainless steel pins and wire, and then just a cement mortar patch. You can see they're scoring each layer. So the next layer will bond to it. And then finishing it is really important to finish it with the same texture as the terracotta. And then that patch will be painted afterwards to match the color of the terracotta. And we talked about Bondo this morning, so I've actually seen Bondo used to patch terracotta on one building, and it's a pretty amazing job. I mean, you can hardly even tell that this urn was patched. But that's the only time I've ever seen it used. The traditional way is with a cementitious mortar. So once you have the patch, or when you have a glazed spall, you want to coat that with a paint to mimic the terracotta. And so there's a couple ways to do that. With a glazed spall, if it's not too deep, you can just sand it off the glaze, remove any biogrowth that you have, and then paint it with a base color, and then using either a sponge or a brush, you kind of get the speckles in there. If it's if the terracotta is maybe just a plain white glazed terracotta and it's close to ground level, and you do that, you'll see a little indentation every place that you've painted the glaze spall because the paint isn't as thick as the glaze. So in that case, you can use some specialty mortars that can be put on really thin to bring out the surface so that it's a nice smooth surface again. Another important part of terracotta restoration is keeping the water out of the terracotta once that it's all restored. And so a lot of times we're adding sheet metal copings to the roof, and we're fixing roofs and gutters so that they don't leak. And it seems like a lot of times I've had discussions, oh, you can't put a coping on there, it wasn't originally there, it's going to look terrible. But this is one example of this building. I think this is 225 Bush. If you look right under the arrow, there's that coping. And it's protecting that whole part of the wall below by putting a sheet metal coping on so the water can't get through there. So you can think of any sky-facing surface as being a small roof, and it really needs to be waterproofed in some way. Repointing mortar joints, just like for stone masonry or brick or anything else, is a really important part of terracotta restoration. And then when you have sky-facing mortar joints, like on cornices, we want to protect those too. And I've used 3 different ways of doing that. One is preformed silicone tape, which you can put over the joints like this. Lead caps are pretty common to set in the joints, or else just putting this is a copper sheet metal cornice over it. Cleaning terracotta. Similar to cleaning other kinds of masonry buildings, you always want to use the gentlest possible method. And it used to be that we used a lot more chemical cleaners, and now with environmental concerns, it's gone much more to just warm water, pressure wash, or even just non-ionic detergent and water and some brushing and elbow grease. And most terracotta cleans up really well because of the surface of it. Dirt doesn't really get in there that much. So usually you can just clean it pretty much with warm water. Here's some different examples of chemical cleaning, and then also microabrasive. And of course, microabrasive, we don't mean sandblasting, which will totally destroy terracotta, but using very low pressure. I think the Jost uses little glass beads. And then there's other types of abrasives up here, walnut shells being used also. When the terracotta is too damaged to repair, like we talked about, you might want to replace it. One thing to be cognizant of seems pretty obvious, is to replace the blocks with the same size blocks and the same joint layout, because if you don't, it'll look kind of odd like this, where the blocks are a different size. One thing that I think most owners don't realize until they've worked on a terracotta building is the schedule. And Jamie can attest to this, but you want to start early because you have to obtain samples from the building, and then you send them to her and she does a glaze match. And you get back samples like this, a bunch of different glazes, and you'll take them out to the building, you'll hold them up to the terracotta, and you'll say, no, that doesn't match, you need more white, and it's too yellow, and back and forth, and then they'll have to make new samples and then fire them, and then you get a glaze match. So that's kind of an iterative process. Then you also we'll talk about specs. There's pre-production testing to make sure the terracotta has the properties that you want. There's shop drawings to be made and reviewed, and then production. So you might be talking 6 to 9 months for the whole process before you get the first block of terracotta on site. These are the different requirements that we have for pre-production testing. A lot of them relate to, well, the first 2, saturation coefficient and compressive strength, have to do with the quality of the bisque. And then you also want to make sure that the glaze is not permeable and it's well adhered and it's not going to craze. Then in production testing, usually we don't require all those tests, only saturation coefficient and compressive strength. And then during production, you're getting these every so often. You can compare them to the pre-production. And if you start to see some big change, then you know maybe you need to go back and test the other things to see what's going on. Just an example of some terracotta shop drawings, markups for the shop drawings. The shop drawings will show the dimensions, the anchor sizes, if there's holes for anchors to go into the terracotta, exactly where they are, how they interface with other terracotta blocks. And then glaze samples. I think something important about glaze samples is I always want to see the whole range of colors, because you can take one glaze mix and put a bunch of blocks in the kiln and there will be a variation in the way they come out, just because I guess of the temperature in the kiln at different points. And so I want to see a sample of what the expected range is, not just one piece. The other thing is these older terracotta buildings, the kilns weren't as regulated as they are now. A lot of them, they were made in beehive kilns, so the terracotta was just all stacked up and fired, not the tunnel kilns, so the temperature was had a lot more variation. So if you look at most terracotta buildings, older ones, you'll see a lot of variation in color from block to block. But if you just pick one of those blocks and get a glaze match, the manufacturer is so much more precise now, it'll stick out like a sore thumb because all your new blocks are going to be one color. So we almost always require maybe 3 colors or 5 colors so that you can get that variation that you see on the original terracotta. A lot of times we will go up to the plant, this is Gladdy McBean, and check the terracotta before it's packed up and shipped. Some of the things that you're checking are the dimensions of it, so blocks should line up with each other. Checking for glaze defects, you don't want to see little cracks or crazing. Make sure the color match and the texture match is good. And then a lot of blocks nowadays are extruded and then saw cut. And you want to make sure that in doing the saw cutting, the glaze is not chipped. So just a couple of examples of terracotta replacement. This was a cornice block that was seriously cracked because these angles that supported the cornice were corroding. So we had new blocks made. Here you can see the new blocks. And then we had new steel made and then filled these cells on the sides with grout and then just lifted it up, put the block in there and let it set. These are terracotta blocks from a church in San Francisco. And here you can see we put in new stainless steel reinforcing to anchor the block to. And then here's the wire ties. And the mullion blocks are going in. And then the wire tie goes around that piece of stainless steel. And this is the building I showed you where we had the problem with the steel columns corroding. These are, I can't think of the name of them, channel anchors. And so we wanted a way to anchor the new terracotta back to the brick. So we installed these stainless steel channels. There's a close-up of them. They're anchored with threaded rods set in epoxy-filled holes. So you put the channels up there. Here's the tube to put the epoxy in the hole, and then put the anchor in and put the nut on the anchor. And then this shows a shelf angle. We had a shelf angle, I think, at every floor line. And then here they're setting the block into place on the shelf angle. And then in this channel anchor will be what's called a dovetail anchor, which is a strap that comes out and has a little pin that goes up and down. And so then here's the strap coming out, and the pin will go down into the block below. And then you take the block above and set it on those, and that pin will go up into the block above. So some key ideas about terracotta. You have to understand how the materials work. So the properties of the terracotta, like that it expands, and how it's used and how the whole building works. You want to diagnose before you repair, perform an investigation. Watch out for water because that's the source of lots of problems with terracotta. And the do no harm, less is more always works in terracotta restoration unless there's some hidden problem or the causes of the failure are not addressed. You always want to make sure to address the causes of the failure. Okay, thanks. Questions?
No questions online, but is there anybody here that has any questions? Wow.
There must be something.
Okay.
I gotta use the mic. See, now I don't want to ask the question. So you said that the terracotta continues to grow. Does the replacement material grow at a different pace or expand at a different pace than the older material? I know it's something I have to be careful with on Adobe, which is different, but you mentioned it.
So the replacement terracotta will also grow. It's still the smallest when it comes out of the kiln. And so one way that we deal with that is say on those columns, we'd have a shelf angle and we set the terracotta right on top of the shelf angle, but underneath the shelf angle, we'd put a sealant joint. And that would allow the story below that terracotta to grow without smashing into the terracotta above. So when you're putting in new terracotta, you always want to be careful to put, typically use mortar joints because that's what's always been done and that's what works. But at certain locations, you want to make sure to put in some sealant joints so it can expand and contract. Well, no, it's sort of, I think it's, Jamie, maybe you know this, I think it's more of a curve. So it expands a lot to start with and then it kind of levels off. So terracotta over time. So terracotta that's old now in an old building, it's done growing. So usually you don't have to worry too much about it. It's just the new stuff that you put in.
Okay.
John, there's another question?
Oh, there's a question. Okay, we'll start over here.
Oh. The question was, does terracotta grow equally in all directions? Okay, so it's, when it comes out of the kiln, it's been fired, so it's really dry. And so it just absorbs moisture from the air. It's not like water leaking in or anything. It's just absorbing moisture from the air, and it's getting bigger. And that's why it grows. So it would be in all directions. It doesn't really have to do with whether it's glazed or not. Yeah, exactly.
So I know you'd mentioned earlier about the difference between concrete and the terracotta. And then you mentioned that for larger repairs, where you're kind of doing a Dutchman repair effect, that you base it with, or you set a ground of concrete and then build up around it. Does that cause problems with it being attached to or reacting differently to the existing material?
Okay, so the place we use mortar is if you're patching just a small, like fist size spall on a block. And if the contractor does a good job of preparing the surface, roughening the surface, putting in mortar, and then a lot of times we'll have them moist cure it so it doesn't shrink so much. Then it's okay. Once it's gotten past that initial installation, after a few weeks or a month, if there's not a little shrinkage crack around the patch, it should be fine. It's not really, it's so small, it's not really going to shrink that much after that. Did that answer your question? Okay.